All right, so I want to talk about logic some more. This is a non-programming lecture, though I will talk about an algorithm at least at the very end. Okay, so what I want to start with is how to think, how to come up with good arguments. So there's two kinds of main arguments in logic. There's deductive arguments and inductive arguments, and I want to talk about both. Computers are really good at deduction. It's like Sherlock Holmes deduction, right? And then induction is something that humans are really good at, piecing together things. Though I mean AI technically is getting better and better, but humans are usually the ones that do induction, and computers are the ones that can do deduction very well in general. So yeah, let's talk about that, because that will give us some firepower and try to answer this question a little bit. Like, what does it mean for an argument to be correct? While I'm thinking about it, slightly less glary now. All right. So deduction is definitely the Sherlock Holmesy way of solving problems. It's when you're making an argument we say is deductive, when it has a conclusion that is a certainty. But what is a conclusion? What is an argument? In general, an argument looks like this. You have a bunch of premises, or premises, however you want to pronounce that, and then you use those to drive towards a conclusion that you're trying to prove to somebody. So a premise just means assumption. So every argument has a bunch of assumptions that they're making, assumption 1, assumption 2, assumption 3, and they're using all those as firepower, driving towards a conclusion. Okay? So this is the idea of just an argument in general, like assume this, this, and this, therefore this must be true. That's an argument, all right, in general. And so we say an argument's deductive when the premises always give you the conclusion. The conclusion is a certainty based on those premises. So that may make no sense, like shouldn't that always be true? But we'll talk about some cases when it's not. But like in general, here's what an argument looks like. There's premise 1, here's premise 2, just like some cloud of an idea. Premise 3, they're all being used to argue a conclusion, right? Conclusion. And that's what an argument looks like. It's like, assume all these things. I'm telling you those assumptions for a reason. Under a universe where those assumptions are working out, the conclusion must be true for a deductive argument. Right? So the conclusion is always true based on those assumptions in a deductive argument. Right? So here's a silly example of deductive argument. It's not even true today, right? So premise 1, assumption 1, it's sunny in Fresno today. That is technically not very true, right? Because there's a lot of clouds today. So, but this is a premise. It's an assumption. Make that assumption. Assume we live in a universe where this is true right now. Assume it's sunny in Fresno, and assume, premise 2, that if it's sunny in Fresno, then Lawton will not be carrying an umbrella today. Okay, those are the two assumptions that we're making, right? Assume those two things. Pretend we're in a universe where both of those are working out. And then our conclusion, based on the premises, this is the full argument, is then, therefore, so Lawton won't be carrying an umbrella today. All right, that's the conclusion based on the assumptions. Okay, and this is a correct deductive argument, because you kind of see that, like, all right, this is like an if-then. So, like, if it's sunny, then Lawton won't be carrying an umbrella. And I know that it's sunny, so I can like plug that into there and get out that I won't be carrying an umbrella. It is correct. Does that make enough sense? That is a deductive argument that is not wrong. All right. So, questions about deduction. Just like a bunch of premises, assume those things, and pretend we're in a universe where those are true. They should give us the conclusion, always, for deduction. All right. So that's what computers are good at, just like piecing things together, figuring out what's true based on your premises. Induction is something humans are much better at than computers. So, by the way, there's something called mathematical induction. This is not that, right? It's a completely different kind of induction. An inductive argument is not when the conclusion is a certainty based on the premises. It's just that the conclusion is very likely. All right, so this has to do with like not just plug and chug like a computer is good at, but more like probabilities, hedging your bets. All right, so that's what induction is for. And here's an example, inductive argument. So here's an assumption, premise. Assume that every time I've walked by that dog over there, it has not yet tried to bite me or growled at me. All right, so that's my assumption, premise. Assume we live in that universe. And then the conclusion based on that assumption is, okay, therefore, the next time I walk by that dog, it probably is not going to try to bite me. Yeah. Do you see how that's not a certainty? Maybe the dog's having a really bad day. Even a perfectly good dog might bite a person if they were like provoked in some way. So we cannot always conclude this. It's not a certainty. It's not a deductive argument, but it's very likely given our knowledge from past experience with this dog. Does that make sense, the difference? Deduction versus induction. All right. So humans are much better at this, making little probability judgments, but I guess AI it's making its way there. All right. So those are two kinds of arguments, deduction and induction. I'll try to focus on deductive arguments because you can't really mess those up. It's a certainty. If you use the assumptions in the right way and this works out, like, it is a correct argument. So those are easier to talk about. But as humans, we use inductive arguments all day long. Okay. So yeah, I think I'm ready to talk about what makes a good argument. How do you know when it's right? All right, so let's talk about validity and soundness. So these are two adjectives that describe an argument, a deductive argument. So an argument can be valid and it can be sound, and soundness is better than validity. It's stronger than validity. Okay, so that means if you have an argument and you know that it's sound, it's already valid because of that. So it's stronger, it implies validity. So yeah, this is going to help us understand this. Like, somebody gives me an argument, how can I attack it and tell somebody that they're wrong in a logical way? You can go after these things. You can say, like, oh no, your argument is invalid. Oh no, your argument is not sound. That's perfect, all right? So that is where I'm going with this. And to lead us there, here is a very, very silly example that I asked ChatGPT to come up with. It helped me. All right, so it's a silly argument about the Muffin Man. All right, so here we have two premises and a conclusion. All right, I will draw a line between them. People like to do that. So I'm assuming these things and concluding these, but there's an issue with this argument. All right, so I think I came up with a story here, and this is what ChatGPT gave me. So in the quaint town of Deauville, renowned for its delightful bakeries, a peculiar incident unfolded that led to the arrest of an innocent citizen, the Muffin Man. So the town was abuzz with excitement over a mysterious theft of the mayor of the town's prized golden muffin, which he kept locked up, a priceless artifact handed down through the generations. All right. So the cops received an anonymous tip last night suggesting that the Muffin Man, the man that we know and love, Jolly Pastry Chef, he was the prime suspect in this crime. All right. Somebody claimed, the tipster on the line claimed to have witnessed the baker near the mayor's residence on the night of the theft. So somebody went and stole the golden muffin last night, and somebody claimed on the tip line that the Muffin Man was near the mayor's residence where it was stolen. All right. And so this is the argument that the cops used in the trial. All right. So let's talk about it. So here are our two assumptions. Assumption one, we know this is true, right? The golden muffin was stolen from the mayor's residence. It is now gone. Oh no, we have to find it. All right. Assumption two, the Muffin Man was seen near the mayor's residence the night of the theft. All right. Those are my two assumptions. Those are two pieces of evidence that I have. And then the conclusion based on that evidence is, therefore, the Muffin Man must have been the thief that stole that golden muffin. All right. And he has to be locked away forever. Is that a good argument? Would you convict if you were on the jury for the Muffin Man? We're shaking our head. Why not? Somebody tell me. What's wrong with it? Yeah, it's just speculation. That's a good word. Any other ideas? Other descriptions of why this argument is not right? Because it isn't right. You can't conclude that. Circumstantial, right, is what the evidence is. But even more so, like these two, like the name of the game is always like, you're telling me these things for a reason. They better like combine in some way to give me this. Does that make sense? That's what an argument is all about. You give me some assumptions, and you better be using those. Otherwise, why did you say them to imply this conclusion? All right, and that's not what's happening right now. You cannot combine these two to give truth to this statement. Does that make sense to us? So that's the issue. So this is circumstantial evidence. Maybe the Muffin Man was just taking a night walk, walking his dog. Who knows? He was just in the wrong place at the wrong time, right? So you can't convict because you didn't see him Like you have nobody witnessing him actually stealing the shiny golden muffin. Okay. Does that make sense to us? That's an issue with the argument, and you can see like those two things do not give us that third thing. All right. And so what I'm about to teach you is some words to mean this. So it just so happens that this is an invalid argument. Invalid. Okay. And so just in one word, we can now say why this is wrong. All right. So I want to teach you what that word means. And here's another one. All right. You may have heard of this if you're a programmer. Here's, again, two assumptions and a conclusion. It doesn't always have to be two, but it's a good example. A computer science relevant example. Here is an argument for you. So all people, assume these two things. Assume that all people with GitHub accounts, GitHub is just a place where you can put your code. It's a public place where you can share code. That's what I do for our Code from Class. Have you seen that? So all people with GitHub accounts are successful programmers. Assume that. And then assume that John has a GitHub account. And then therefore, we're concluding that John must be a successful programmer. Does this argument check out? We're not so sure. What are your thoughts? Somebody tell me. Do you think it's a good argument? Why or why not? Can you conclude that from the assumptions? Very good. Yeah, so this is doesn't mean you're a successful programmer. There's plenty of students who are just using it for a class, and they're just doing it because the professor's telling them to do it, right? Doesn't mean they're successful yet. So we take offense to this first assumption. That makes sense to us. But at the same time, in a universe where we assume this is actually true, these two things, do we get this out of it? If you were to assume those two things, just like without complaining, would these two combine to give you this? Yes or no? Even though we maybe don't agree with the first one, if we were to assume it though, would it feed in and give us that last conclusion? All right, too shy today. We're going to buy clicker then. Whee! I need thoughts. So here, go to buy clicker and assuming what I just said, assuming these two things, do we get that out of it? A for yes, B for no. All right, give you 10 seconds. If you were to believe that you were in a universe where those two things were true, does it give you that? A for yes, B for no. I know it's too early in the day, but you got to humor me. Thank you. All right, I think we do agree. Thank you, even though you're too shy to tell me. I appreciate that. So yeah, if you were in a universe where you were assuming these two things, like if this really was true, then you can kind of like plug in John because has a GitHub account, and then get out that he has a successful programmer. Does that make sense to us? That's kind of interesting. So like if we were to assume these two things, we would get this out. And so that's an example of being valid. So the argument is valid, but we take offense, right? We don't believe this first assumption in the real world. It doesn't actually make sense, right? So it's valid, but unsound. So these are the terms I'm trying to teach you, right? So I'll give them their real definitions now, but these are two issues, right? The argument can just be invalid to begin with, or it could be valid, but not actually sound, all right? Still doesn't make sense because like we don't like this assumption. So that's the difference. Let's talk about it. All right. So in general, deductive arguments kind of look like this. It's usually like you give two things because they can be used together in some way. Like a lot of what I've just shown you, if I can draw a straight line, is the following. It's like, all right, premise one is like, if you give me A, I'll give you B. Like I have an arrow. And then premise two is like, all right, I'm giving you A. And then like your conclusion is B. And that works out usually because you can plug in the A there and that will get you out the B that you can conclude. That's a very good valid argument. All right, so an argument we say is valid, and that gives you that one there. An argument we say is valid if it's impossible for the premises to be true and the conclusion to be false. So it's just another way of saying like, all right, these always, if we assume that we're in a universe where this works out, we always get this guy. That's what it means to be a valid argument. So that's this. This is valid because if we assume those two things, we really do always get out that John is a successful programmer. Okay, so that's that one. That's validity. And though it doesn't have to be true that these premises really work out in the real world. So if you have a valid argument, it may not also be sound. All right, so we say that an argument is sound if it's valid first. So you need that for sure. It's got to be valid. It's got to check out. And then also all the premises are true in this universe. Okay, does that make sense? That's a stronger requirement on an argument. Any questions about those two terms? Argument's valid if it's impossible for the premises to be true and the conclusion to be false. So another way to say that is like always the two assumptions or whatever, however many there are, always give you the conclusion if you assume them at least. And then soundness means that works out, it's valid, and then also the assumptions were correct assumptions for our universe. Okay? All right. So yeah, stay on the ByClicker page because now I have questions for you. So here, I'll let you guys get into groups and talk about these. I'll give you like 2 minutes for the first one, and then I have a few more. I'll just give you less time. Please do attendance. I'll stop that after this first question if I can remember. But here is my question for you. Here is an argument. Let me talk about it, and then I'll send you off. So, and then here's the definitions, by the way. Here's my argument. Two premises and a conclusion again. So assume all birds can fly. Assume bats are birds. Therefore, conclusion. Therefore, bats can fly. That's the argument. All right. So please get together with the people sitting next to you, say hello, and try to tackle this question. So tell me if it's valid only, valid and sound, or neither. All right. I'll give you 2 minutes. Questions about the question, though? You good? All right. Try it. You got the definitions there? See if you can figure it out. It's a good argument. How good is it, is the question. What do you think? One more minute. Does it check out? Does it all work out? Is it valid? Or is it also sound? All right, sounds like our conversations are dying down, so I'll give you another 20 seconds to get your answer and finish up your discussion. One. All right, let's see what we're thinking here. Look at us. Nice. It's a beautiful graph, but it looks like we're thinking A. And let's talk about it. I think, let me look at it. Yeah, that is the right answer. It is valid. Only valid. Can somebody who chose A tell me why? Why they said so? Oh, yeah, I haven't heard from you yet. You go, please.
I mean, birds can fly.
Yeah.
Bats can fly, but bats aren't birds, they're mammals.
Good. Yeah. So you do get it if you assume you're in a universe where this is true. It does work out. That's exactly right. So bats are birds. If you assume that all birds can fly and bats are birds, you can plug bats in to that one and kind of like get out the fact that bats can fly. Does that make sense to all of us? That's what makes it valid. But then it's not sound. Can't be sound only, by the way. You can never be B. It's not sound because all those premises are true. I didn't know this because I'm not a biologist, but I had to learn this when I gave this question. Apparently, bats are mammals. They are not birds. Do we know this? So it's not a correct assumption to say that bats are birds. So it is not a sound argument. But if you were to assume that you lived in a universe where this actually was true, it does check out. It is valid. Does that make sense to us? Any questions about that one? It's interesting, right? So I have a couple more. So now we can go a bit faster now that you've tried it. But here's another argument. All right, again, two premises and a conclusion. I'll restart the question. I promise to stop that. Boop. Here's your next argument. So assume all snakes are reptiles. Assume all lizards are reptiles. Therefore, all snakes are lizards. All right, there's your argument. See if you can figure out which of these is correct about it. All right, I'll give you just a minute this time, so please discuss. Figure it out. All right, that's my timer. Take another 5 seconds to click an answer, please. What did you figure out? Let's see what we're thinking. This one's a weird one, isn't it? Yeah, we're not quite sure. And that's why I'm asking these of you before I ask it to you on a test, right? So, okay, we know, first of all, that soundness needs validity first. So, B is off the hook. You cannot have just B. All right, that's impossible. But all the rest now are the things we need to check off. So let's figure this out. I guess if we deal with validity, if it's not valid, it can't be sound, right? Because it needs to be valid first to be sound. So like if we check A first, that'll either tell us like, all right, should we look for C or can we cross off D or circle D? All right. So let's figure this out together. All right. So all snakes are reptiles, and then all lizards are reptiles. We're trying to use that to give us this. All right. So thinking about this in terms of the arrows, kind of like this. What is this telling us, this first assumption? It's like, all right, assume that all snakes are reptiles. It's like, if you give me a snake, I'll give you proof that it's a reptile. That's kind of what it's saying in an arrow form. Does that make sense? You give me a snake, I'll tell you that it's a reptile. That's kind of what the first thing's saying. And then the second one's like, all lizards are reptiles. So like, if you give me a lizard, then I'll tell you that it's a reptile. 2 arrows. Does that kind of make sense what those 2 assumptions are telling us? Like, that's what it's saying. You give me a lizard, I can prove to you that it's a reptile because I'm assuming that, right? And then we're trying to use those 2 to combine together in some way to say that therefore all snakes are lizards, which we can't get, right? There's no way to like, I just know that snakes are reptiles and lizards are reptiles. I know that they're both reptiles, but there's no way to like run this arrow like backwards. Like give me a snake, show that's a reptile, and then show that that reptile is then a lizard. Do you see how that would be an arrow backwards that we don't have? Questions about that? It's weird, but that implies that it's not valid. Do we see that? Like these do not give us this. It does not work out, so it can't be valid, which means it can't be valid and sound, which means the only right answer is neither. D. So good job if you got that one. This one was a trickier one. Are there questions about this? Because the majority of us got this wrong. Do we see the answer now, though? Yeah? Okay. Please shout out. If you don't, I can re-explain the whole point of these questions. So yeah, I got more. I got more until we get it, all right? We'll figure it out. Or at least you can study these after class. Here's my next one. There's the definitions again. So here is another argument. Every time Dave orders pizza, his neighbor Bob can smell it from his house. I'm going to make pizza tonight. I'm excited. So we got that. Assume that. Assume that Bob smells pizza right now. Conclusion, therefore, Dave must have ordered pizza. All right, that's my argument. Try again. Valid, sound, both, or neither. Two assumptions. Assume we live in those universes. Do we get that? Then also, are those assumptions correct? True assumptions in the world. Yeah, discuss. It's very loud. All right, another few seconds to enter in your answer, whatever you were thinking. Let's see if we agree this time. Ready? All right. Oh, we're still not sure. Interesting. We think it's probably not D, maybe, though? Some of us keep picking B, though. I need to tell you, B is never the answer. Cannot just be sound. It has to be valid and sound. Do we see that? It's part of the definition. Cannot be B ever. All right, let's talk about this. So, okay. Every time Dave orders pizza, his neighbor Bob can smell it from his house, and Bob smells pizza right now. So, all right, what does this give us in arrow form? I guess we should figure out. Like, all right, every time Dave orders pizza, his neighbor Bob can smell it from his house. So, like, it's like if you give me the fact that Dave has ordered pizza, if Dave orders pizza, then we can get out that Bob smells that pizza. Do we all agree that that is the arrow equivalent of that assumption? It's like, you give me that Dave orders pizza, I can show you that Bob smells the pizza. It's close enough. He can smell it. And then Bob smells pizza right now. So then we're trying to combine these two to get out this. Do we get it? We're confused. We're not sure because of the answers that I saw. But it's got to work like this. It's got to be, you give me the first thing, and the arrow leads you to the next thing, and that's what you conclude. That's actually not what we're doing right here. We're giving this, we have this, right? And we're trying to run the arrow backwards again. That does not work. Does that make sense? That's not going to work. So we know that if Dave orders pizza, Bob smells that pizza, but it doesn't mean that the pizza Bob is smelling has to be Dave's. That would be running this backwards. It could be his other neighbor on the other side of him bought pizza. Does that make sense? This is not valid because that would be trying to run this backwards because we have this side and trying to get this side. The arrow does not go that way. Does that make sense to us? So it cannot be valid, which means it must be neither because like that one's off the table. So it's D again. Do we see it now? Are there questions about it? So I want to make sure I'm answering your questions because you got two of these wrong now. It's something to study. It's a hard idea, but I want to make sure we're understanding it. questions about this before I move to the next example? See how the arrow is going that way? You cannot run it backwards. It's not right. I got one more. Redeem yourselves. Let's do it. Valid or sound? Two assumptions and a conclusion as usual. Let's try it one last time. Let's see if this one's a good one. Assume all mammals are warm-blooded animals. Assume dolphins are mammals. Therefore, dolphins are warm-blooded animals. Okay? Valid if it all checks out, it all feeds into the conclusion. It's sound if that is true, and then also the assumptions are good assumptions in this current universe where we live. All right, so another minute to discuss. Try that one. I can't trick you anymore, right? Let's see. Is this one easier? All right, take another 5 seconds to enter in your answer. What were you thinking? Let's see. Oh yeah, look at us. We agree on something now. Look at us. Good for you guys. So let's see. I think the answer is actually C. So pat yourself on the back. We're doing it. All right, so here. I think we see the name of the game now. So all right, what does this give us? What does this say? All mammals are warm-blooded animals. So it's saying, like, you give me a mammal, I'll give you out the fact that it's a warm-blooded. Yeah? And then we're saying that dolphins are mammals. So we know that dolphins are mammals. And we're trying to conclude that therefore dolphins are warm-blooded animals. Is this valid? Is now the question. I think it is. Because we know that dolphins are mammals. We can plug that fact into here. Get out the fact that dolphins must have been warm-blooded. Do you see how that's the correct direction for the arrow finally? It is going to check out. That gets us out the fact that dolphins were warm-blooded. That gives us the conclusion, so it's for sure valid. And now the question is it also sound? We know that it can't just be sound. So is it also sound is now the question. So are these correct assumptions? Do they check out in this universe? Yes. Mammals are warm-blooded animals here on Earth. And then dolphins are for sure mammals. By a weird quirk of the way that they grew, right? So they went back into the water. So there is, that means that these are true assumptions and it's also valid. So now it is valid and sound. So C. Good job. Any questions about this question? I think we're getting it now. These are deductive arguments. So computers are sometimes better than humans are. And we have discovered that today. But now we're good at it. We have some practice. Go back to these as you study, and I think it will all come to you. I think I want to go to a different topic now. Are we ready to switch gears? Any last questions about this stuff? All right, I want to talk about that arrow because we used it a lot. That arrow thing. We can talk about that in logic. We can make that arrow a real logical symbol, right? It has to do with if, because we know that English is ambiguous. So let's make a symbol for meaning like if something, then this other thing. Like that's what I've been doing secretly for you anyway. So let's talk about that. So let's say like we want to logically specify the fact that Dad says, "I'll give you $20 if you mow the lawn." Right? We want to set that in stone and make sure that that is logically specified so that we don't get like cheated out of our $20. All right. So by the way, this could be anything with an if as an arrow. I've been using that already. So like This is kind of a backwards arrow. It's like Dad saying, if you mow the lawn, you do that first, and then I'll give you $20. Does that make sense? The arrow's going that way. You do the job, I'll give you the money. So that's that. And so let's come up with all the ways, all the combinations of like us mowing the lawn and then Dad giving us $20, and let's see like when it is true that like this is like a correct statement. Like I'll give you $20 if you mow the lawn. If you mow the lawn, then I'll give you $20. Either way you want to say it. So we want to like try all the possibilities of mowing the lawn and getting $20 and see when this is a true statement, right? When this arrow is a true statement. And I kind of want you to think about it backwards. It's easier that way. I want you to think of it being a false statement when Dad lied and you were lied to. Dad cheated, so you were lied to. That will help. All right. So that will give us that. So under what conditions would we feel cheated if we didn't get that $20? So here are your options. If you mowed the lawn and then you got $20, do you feel cheated by Dad for saying, I'll give you $20 if you mow the lawn? You mow the lawn and you just got $20. You don't feel cheated, right? You got your money. You did the work, you got your money. Dad was not lying to you in that situation. I'll come back to this one. If you did not mow the lawn, but you still got $20, do you feel cheated by Dad saying, I'll give you $20 if you mow the lawn? No, you got your money for free, right? You got free money. You didn't mow the lawn, but you somehow got $20, so Dad was not lying still. He just gave you money because he felt sorry for you, maybe. I don't know. All right, if you didn't mow the lawn, but you didn't get $20, do you feel like you were lied to when Dad said this? No, you just didn't do your end of the work. So you don't feel like cheated there. The one time you feel cheated is right here, right? If you mow the lawn, but you did not get $20, Dad was for sure lying to you when he said this. Does that make sense? That is the one case where you totally feel cheated and you go get your lawyer and you sue Dad for $20, okay? Or you go get Mom. That's the idea. So that leads to a logical symbol, right? It's called implication. It's just short for like an if-then in logic. If something is true, then some other thing is true, right? So it's a logical if-then. Think of it this way. If A is true, then B is true. That's kind of what it's saying in shorthand. Then B is true. Okay. So yeah, it looks like this, this little arrow thing. It's also called a conditional. It's called implication, all right? It's an if-then statement. It's called a conditional in programming, but it's more or less the same idea, all right? So it looks like this. If you have the if part on the left, then you have an arrow, and you have the then part on the right, okay? That's what it turns into. And so we just discovered the truth table for an if-then statement. So like A was mowed the lawn, B was got $20, and then this was if A then B. If you mow the lawn, then I'll give you $20. That's what Dad was saying. And we determined the one case where it's a false statement, where somebody lied to us. That's this one, where we did the thing. We upheld our end of the bargain, but we did not get the conclusion, right? Our payout. That's the one time where it's false. Every other time, Dad was not lying to us, and we consider that to be true. Does that kind of make sense? That's going to be the truth table for implication, for the logical if-then statement. Okay? So yeah, it's true everywhere else. And so, if somebody's trying to, if you're trying to prove that your implication is a true statement, that you're not lying when you said if A, then B, then you just have to show that you're not in this case, right? You have to show that you're not in this case, because any other case means that you're true. So just make sure that, you cannot, uphold the bargain and still not get the payout, because that would make it false, right? Another way to think of it is, if you give me A, then I must give you B. That also scratches out this part. If I give you A, then you must give me B. Otherwise, you were lying to me. In every other case, these ones down here, it's kind of we call it vacuously true, because it's you didn't do your thing anyway. Anything goes at that point. So yeah, that's the idea. That's the situation. Any questions about that symbol? Because I've been using it. I've been using the arrow before, but now we kind of get it a little better now. Now it's logical. And now I can talk to you about why deduction, why validity makes sense, all right? Why we defined it to be that way. So here's a silly example. This is the standard deductive argument, by the way. You'll see it in every philosophy class. So assume the following. Assume that all men are mortal, and then assume that Socrates is a man. And we're trying to conclude that, therefore, Socrates is mortal. And this is a valid argument, because you can plug in Socrates, because he's a man, into this, and get out the fact that he must be mortal. Yes, that's a valid argument. And if you turn it into implications and things, it looks like this in symbol form. It's like, all right, you give me a man, I'll tell you that he's mortal. Cool. And then here I know that I have a man, Socrates. Yeah. So that's what this really looks like. It's saying like, if man, then mortal. That's what that symbol means. So there's your A, there's your B. And we're claiming that man is true, and then we're trying to conclude that therefore mortal must be true. Does that kind of make sense to us? That's what we're doing. So I can show you that this is valid without having to think. We can use the truth table. It's like, all right, if we assume that this is true, and then also this is true, then we have to prove that we're always in a case where this is true. That's kind of the idea, right? I'm going to show you that the conclusion follows from the truth table. For that symbol, for implication, the conclusion follows from, that's supposed to be an O, the truth table for the implication, for logical implication. Okay, so let me prove that to you. Let's see, where are we? I guess I'll just use a different color real quick. So assume that this is true, right? Assume that, how do I want to do this? Yeah, assume that man implies mortal is true. So that means we're in one of these three cases, right? This one, or this one. Because like there's that if A, then B. Assume that we're in one of those, right? Assume that it's true. That means we're in one of those three. We're not in that other one, in the middle one. We're in one of those circled ones. Assume that man is also true. So where are the cases that man is true? That's the A part, right? That's these. This one and this one, right? So that like means that we're only in, right? Do you see how those taken together means that it's only true when, like, we can't be here because it's false, and I can't be here because the other thing is true. Like, we're only in this first case. Does that make sense to us? Those are the only times that both of those were true in the truth table. The A was true, and then also the A part was true, and then also the implication itself was true. And then we just have to show in, like, all the cases where that all checks out, that the B part was true, the mortal part was true. So is that true for this one case that we've just determined that we must be in? Is B also true? Yeah. That's why it's valid. That's why it's valid to do that kind of conclusion. All right? That may not make a ton of sense right now, but like that's the reason that validity is validity. All right? It just follows from the truth table that we've given for implication. It's like assume that you're in a universe where that's true and that's true. Just show from the truth table that like in that other column, it must be the case that that other side is true. Okay? So I think that's what I wanted to say there. I hope that made a little bit of sense. Any questions about that? And then, like, the last thing that I can show you about this is we can make a computer think deductively because we can totally make a circuit for implication. I told you that you can make anything out of any truth table out of ands, inclusive ors, and nots. So it just so happens that A implies B is equivalent logically to not A or B. Let me show that to you. Whee. And we can totally make a computer now, a circuit that does that calculates implication. If something is true, then something else is true. Isn't that interesting? So not A is false for this one, or with B, that's still true. That's true. That checks out. Not A is false, or with false. That's the only time it's actually false, right? And then not A, false knotted becomes true, or with anything is still true. And same for the last one. True, true. So it is equivalent. That's neat. And so that means we know circuits for that. We can take an A, take a B, feed it all in, and do some magic, some knots and some ors, and get out electricity that tells us like when the implication is true, which is kind of neat. And so we can have a computer think for us based on that idea. Okay? That's coming full circle, I guess. Teaching a computer to think. Artificial intelligence. Any questions about that? I like it. It's a fun idea. Alright, so yeah, the last thing that I want to talk about today, I guess I have two topics. Last two topics. The first one is called framing, and I accidentally spelled it farming the first time that I made these slides, and I'm just going to keep that forever because I thought that was funny. So framing is an idea of, it's like somebody's frame of reference, somebody's point of view. I'll try to answer this for you. It's like when you're arguing with other humans, you might be like feeling like you're yelling at a wall, and like this other person, they're not seeing your point, but to you that point is so obvious. Why are they not getting it? Here's the answer. All right, we have to talk about that. At least the frame of reference is what I'm trying to say here. It's just your worldview, how you view a situation. All right, so your frame of reference shapes how you view the world. Like you have made some assumptions in your mind that like you hold to be true, and that influences how you like deal with anybody's arguments, how you make your own arguments. All right, so it shapes how you view the world, and also the assumptions that you are willing to make. All right, so that is very key. It's just like the way you've been raised and things like that. So another word for that is your worldview. Your worldview. And then it has to do with like the way that you'll interpret words, like the connotations of words. If you remember that word from English class. Connotations, all right? Rather than the denotations. And so the idea is, the second you like have told somebody what the frame of reference is for a certain argument, like you've already won. So this, if you can control the frame of reference, like the way that somebody's viewing your argument, then you can control the assumptions they're willing to make, and they can probably side with you. Right? So you can control the entire argument at that point. And this also tells us, though, why some people can have the exact opposite viewpoint as we do, but they cannot still justify it because of the things that they're allowing themselves to assume. Okay? That's the idea. So here's a silly example of that. It's just an example of worldviews, right? So here's some frames of reference, very, very simplified. I'm not trying to like start a fight in this class. But here are some examples from politics, because politics should be very familiar to all of us, of like, here are some topics framed from a left-wing, like a liberal point of view, and from a right-wing conservative point of view, the same topic. Do you see? You just read both columns. Do you see how the way that one side views a topic, like, gives it some connotations, some different connotations than the other side? And that's going to influence, like, if you're having an argument with somebody that's the opposite side of the political spectrum as you, the assumptions that they're willing to make, the things they're allowing you to, they're going to concede to you. Do you see that? And that's why you feel like you're arguing at a wall, because these other people that believe this opposite thing, this is what they're assuming. And so you're not going to get them to change their mind because of that. See that? If you can influence them, if you can bring them to your side, then you can use different words, and now suddenly, like, you've won the argument. Because those words are powerful. All right? Any questions about that? It's an unfortunate fact of being a human. We're not computers. We think inductively, not deductively. So, yeah, that's what I wanted to say about that. That's why sometimes you might have the best argument in the world, but still it won't get through to somebody. All right. Or maybe vice versa, you're wrong. Maybe your worldview is the wrong one. Who knows? So, yeah, that's what I want to talk about there. Just a quick slide about that, because we will be arguing in real life. And now you know, if you didn't already. Yeah, the last topic I want to talk about today is called state machines. It's a fun one. So it's just a neat way of writing code. This is finally being tied back to computer science in some way. So let's talk about one way to break down computation. It won't always work out this way, but it's a cool way that is very powerful. If you can get your problem to turn into this thing called a state machine, it's very easy to program it, and it will usually be correct. All right? So yeah. In general, the way to break down computation is to make an algorithm, right? An algorithm is just a sequence of steps. Algorithm. It's a sequence of steps to solve a problem, and like, if you have a large problem in front of you, maybe you want to break it down into a bunch of mini algorithms. Like first do this thing, then hand it off to this thing, then do this over here. So, and then maybe that's your final end goal. We can put in Rainbow. That's kind of how you want to do things, but let me show you one way to start breaking it down, right? Because that's just a new idea. So a state machine is one way of writing code. It doesn't always work for every problem, but if it does, if you find that it works, it's a cool one. So a state machine, like all things in computer science, it's a bunch of circles and arrows, all right? So these are examples of state machines. These are circles, these are arrows. These are, I guess, supposed to be circles. Those are arrows. So I'll zoom in and talk about them. But the idea of a state machine is that your program is always in some state. You're modeling the world. The world's always in one state or another. And then you can move around between states via these transitions, these arrows that take you between circles, okay? So here, let's talk about this. This is a silly example, this first one. It's a state machine that models a very boring person, all right? So there's 3 states that this boring person can be in. They're either in the work state, the home state, or the bed state, okay? I hope that makes sense. And let's say that like they're born at home, and so they start their life in the home state. You can talk about the starting state when you turn on the program that models this. And then, all right, so you're at the home state. Maybe it's a work day, like it is today. And so you want to go to the work state. You only have one way to get there. You have to follow this transition. Take the train. You have to get to work through that, and that'll move you into this state. All right, there's no other way. You don't have a car. You must take the train. All right. Now you're at the work state. It's time to go home. And so you want to transition from here to here. Again, you're going to follow this arrow, this take train transition. There's no other way to get home. Now you're back here. All right. You kind of see what the name of the game is. It's boring, but it makes sense. And then maybe it's bedtime after dinner. You want to transition to the bed state from the home state. So you follow the sleep transition. And then now you're in the bed state. Then maybe you wake up and you're back in the home state. It's time to go to work again. All right. So if you can break down your problem like this, you get some very strong guarantees, don't you? Do you see how it's impossible to go to sleep at work right now? If you model it this way, it's impossible because you do not have an arrow that way. You see that? Just the omission of that is very powerful. Okay, super nice, super cool. What else was I trying to say here? And like, there's only one way to go to work. You have to take the train. There's no driving. There's no Uber or something. Okay, and so you can still model this in any way. You can do this in any order. You can go like, all right, maybe you go home for lunch, then you go back to. Oh gosh, don't help me out, PowerPoint. Go home, go to work, then you go home for lunch, and then you go back to work, and then you come home again. That's okay to do that. You just like wrap back around a couple times. And then same with like, maybe it's the weekend, you stay at home twice, and then you go back to work. Oh man, PowerPoint has updated and has done something weird every time I draw things that look like circles. But you kind of get it. Like, it's telling you what you can do. And so here's a better example now that we understand the process. So this is a state machine model for a ride-sharing app, like for Lyft or for Uber. So let's say that you're, like when you turn on the app and you request a trip, it starts in this state, this trip requested state. Like this is maybe what's really going on under the hood. I'm going to show you how powerful state machines are based on this. So, all right, we started the trip requested state. We're trying to get a ride somewhere. And the very first thing the app is going to do is hit our credit card, right? We have to go to the payment requested state and like make the payment process. Does that make sense? Like that's the only way we can ever get a driver assigned to us. Does that kind of make sense what's going to happen there? Like only if the payment succeeds do we end up having a driver coming towards us. Otherwise, if it fails, we go back to the request state. Like we have to try over again. Gotta do it again, enter a new credit card. Keep on going. And so like, do you see how you are not getting a ride if you program this into a computer? Like it's powerful. This is what Uber's probably doing. Do you see how you cannot get a ride until you've paid? You're forced to go in between. That's super nice. If you could program this, and there's a way, you have a very strong guarantee about your program right now, don't you? If you can conclude that you made exactly this inside the program, you can prove to your boss that, all right, nobody's ever going to get a free ride. That's very, very powerful, right? And so maybe now you're in the driver assigned state, like dude comes, picks you up, you take the trip, and then the driver goes and becomes unassigned, goes to other people, and like there's some final like hit the credit card for real this time kind of thing, end the trip, or like if you cancel, there's some weird way to get a driver unassigned as well. But like this is good enough, right? This is a state machine that more or less models the process, and you see based on what you can do, the places you can go. All right, it gives you some very strong guarantees. You cannot like the trip doesn't immediately end after you request the trip. Like that would be a bug, right? If you program this, that could never happen. You cannot get a free ride because you must go through the payment stage, all right? That is very, very cool and very, very powerful if you could program this. Any questions about that? Not all problems break down into being state machines, but some do. And so here's just some silly examples to end off on, and then I have one good example. All right. So yeah, in general, if you can find it, you can find that your program matches a state machine. You've noticed that you can break your program into states and actions that move you around those states. Okay, that's the goal. And so here's just a silly, let me turn you guys into a state machine now. So if you are a student in my class, let me say that I think of you as like a two-state machine. You're very simple in this class. You just have two states, learn and practice, right? As far as I'm concerned, all right? And you're just going to alternate between them. There's you start your state in the learn state because I have not assigned anything yet. So like there's a concept of a starting state and an initial state. You start off in the learn state on the first day of class. And then like as I assign things, you move into the practice stage. And then you can have transitions that remain inside of the certain states. Like as long as you're working on the assignment, keep staying in the practice state. And then when it's time for lecture again, go back to the learn state. And like as long as the lecture is going, in theory, you're staying in the learn state, right? So that's you, as a nutshell, in my class. All right, so like you alternate between the things. You can stay within the state. You can take a transition like that. But that's like a model. I hope that makes sense. And then you can talk about like what's the starting state. You could have only one starting state. You start in the learn state. And then if you draw a double circle, that's called a final state. That's like where you want to end up with a successful run of your state machine. So your final state in this class is going to be the practice state. That's the final state. We draw a double arrow like that, final state. Because on the very last day, you're taking the final exam, right? And like there's nothing left for me to teach you. And so like you're going to end, you're going to turn off your state machine as a student for this class in the practice state. I hope that makes sense. Okay. So yeah, any questions about state machines? They're just a bunch of states and transitions that move you around between the states. Some programs can match this way of working. Are you ready for a legitimate example that involves code, more or less, that you could turn into code, like that would do something cool inside of the computer? All right, so here's a fun example. It's going to count words. All right, I'm going to make a word counting program or a word counting state machine. It'll count the words in a sentence. Let's say that the user gives you a sentence. You like tell them type me your sentence or type me out your essay, and I'll count all the words in it. This is technically the algorithm that like Google Docs and Microsoft Word is using, by the way. So like it is legitimately cool to pay attention to. And so like the user gives you some big long string of characters in the answer variable, like in Scratch. And then it's your job to go through the characters and count how many words were in the sentence that was given to you, right? And so I'm going to claim that you can solve this problem very cleanly with a state machine, okay? And you might be wondering, like, isn't it easy to count words in a sentence? Like, what if the user, like, just says, hi, mom, hello, and, like, that's it? Just, like, count the spaces, right? You might say, just count the spaces, add one. You counted the words. I don't even need a state machine. Well, let me show you why you're wrong. What if the user was malicious? They're like, all right, 3 spaces, then hi, then space, then mom, then exclamation point, then another space. See how that all goes out the window at that point? You still want to count the words in this. Let me show you how. The state machine will do this. It will cleanly solve this problem, all right? So yeah, what we're going to do is the way that we're going to run our state machine is it's going to be run based on the characters. The characters that we see, we're going to look at each character one by one in this sentence and feed it through the state machine. That's what's going to cause the transitions. And we're going to keep track of whether or not the character we see right now is a white space character. And by white space, I mean just like blank space, like either a space character, like hitting the enter key or the tab key. That's all spaces. We call that white space in computer science. And that's going to turn out to be the answer here. Noticing that white space separates words, and that every character that we see that is not white space is either part of an old word that we've already seen, that we already counted, or the start of a brand new one. All right, that's going to lead us into the answer here. And so we're going to run each of these characters through a state machine as this one. All right, there's going to be 2 states in our state machine. I think this is enough room. I'll do my best. We're either going to be outside of a word, or inside a word. By the way, this is an algorithm that I learned when I took my first programming class at Fresno State. So if you guys ever become a teacher, you have to teach this now, all right? We have to pass it along, okay? So here, we're either in outside of a word state or inside of a word state. And at the beginning of time, we haven't looked at any characters yet, so we're going to start in the outside of a word state, right? We're outside of any word. We haven't seen anything yet because we haven't looked at any characters. That's going to be our initial state. And then we're going to transition based on what we see. All right. So we're going to run each character one by one. Let me draw an arrow here. Hopefully I can keep that arrow moving. So like the first character we see is a space character. If we see a space character, are we outside of a word or inside of a word? High, the H and I of high are for sure inside of a word, but a space is not, right? We're outside. Yeah? I hope we see that. So like if you ever see a space character when you're in the outside of a word state, and we are right now, then you are still outside of a word. See a space. I hope that makes sense. Yell at me if it does not at any point. That's my purpose as a teacher, right? To be yelled at. So, okay, if you see a space, you're still outside of a word. So you're still outside of a word, still outside of a word. But the second you see an H, that's a non-space character. Does that make sense as to that you are now inside of a word? You've now moved. So like if you were here and you just saw a non-space character, you are not outside of a word anymore. Yeah? See a non-space character. So now we're in here. We see the H of the high. And if you see the I as well, that's your next character, you're running it through, you're still inside of that word, right? You're still inside of a word, as long as you keep seeing non-space characters, as long as that word is. See non-space. Does that make sense? And then the second you say space again, or hit enter, or whatever, hit tab, you were inside of a word, now you're outside again. Yes? So you see a space, it moves you on that way, see a space. And so there is a way to program this, and like then you see the M of mom again, you're outside, now you're inside. Now all we have to do is hook this up to a count variable to keep track of how many words we've seen. So like count starts at 0. I claim that one of these transitions, one of these guys, is the one that notices a brand new word. And we just always want to count the first second we see a brand new word, because that will save them all eventually. So like, can anybody see which of these transitions is the one that notices a brand new word? Because then we should be paying attention, like wake up and add 1 to our count variable. Does anybody see the one that's going to notice a brand new word? That could be right, technically, if you had a space at the end, but what if your string was just high? You start outside, go to inside, stay inside, and you never counted because you never went back outside again. Like you were saying that one, right? So yeah, we'd never even get to that one, but you still had one word. Does that make sense? So not quite that one. Anybody else? So it can't be that one. That one does not notice a new word. Which one is it? If you keep seeing spaces, and you're still outside of a word, that never, like you're not even in a word right now. Yeah, so it can't be that one either. If you're inside of a word, and you see another non-space character, it's like, that's part of the same word that you were already in, right? It's like you saw the I or something. That's this, you were inside already and you saw it again. So by process of elimination, it's this one. All right. If you were outside of a word, you just noticed the non-space character. Do you see how that must have been the start of a brand new word? That's going to do it. That's going to be the one. All right. It will be this one, and I'll prove it to you. So if you just keep track of every time you see a non-space character, like if you ever follow that transition, like you were outside of a word, but now you're suddenly inside, that's the first character of that brand new word. So just do a +1 right there to your count. And let me walk you through it. So, okay, let's run the state machine now. I'll prove to you that it works, even for this weird looking string. So here, we start out outside of a word. This is our state right now. We're outside. We have not looked at any characters yet. And now we see the first space. Run it through. That was a space, so we stay outside of a word. We're still outside of a word. And then we do that for the other 2 spaces still. Like we see a space twice. We're still in the outside of a word state right now. Okay? You follow me so far? So we're outside of a word right now, but then we see the H. So we were here, and now we follow this transition to here. Do you see how that was the one that noticed a brand new word? Now we're suddenly inside of a word. That was the first character of it. We're in this state now. We followed this transition, so we better add 1 to our count. 1. And so now we're sitting here, and as long as we keep seeing non-space characters, it's part of the same word, like the I. We follow this transition, stay there. Does that make sense? Still inside that same word. Nothing has changed. But then you see something to separate that word, a space. You were here, but you must now follow this. You see a space character, now you're outside of a word. See that? Solid space, now you're outside of a word again. But then you come around and you see the M. So you were here, but you just saw a non-space character, so you don't stay there. Now you're inside of a word, you follow this transition. Do you see how the M was the start of a brand new word? That's the right one. Now we add one to our count. Count should now be 2. And then now we're inside of a word, as long as you keep seeing non-space characters like the O and the M, like you stay inside of a word. You're still inside of that same word that you're working on. Exclamation point counts as a non-space character, so you're still inside of a word. And then, if you see one more space, it doesn't really do anything, doesn't matter, but it's going to transition you just in case, right? It's going to move you from you were inside, but now you saw a space, so you must be outside. So the state that we end on is going to be the outside of a word state. And just by always remembering when we follow this transition to add one to a count, we have correctly counted the number of words in this weird-looking sentence with a number of spaces that is silly. Does that make sense? Are there any questions about that? That's a cool algorithm, I think. And this is secretly what's like going on under the hood when you use Google Docs and it's counting your words or whatever. This one will never mess up, regardless of how many spaces, because of this. That is the secret. And so there is a way to turn this into a state machine, all right? But that is not where I want to go right now. I don't think. Let me double check. I don't think I want to do that because that would take an insane amount of effort. What lecture is this, by the way? Yeah, I think we're good. So yeah, there is a way to turn this into a state, like the state machine, into a program. What you do is you make like a variable that keeps track of which state you're in right now. Like, am I in this state or this state? And then as you read each character, you like change your variable. Like, all right, my state was outside of a word, but like that's state number 0, and now I'll move to state number 1 or something. It's just going to be a bunch of if-elses, if-else blocks. It's like, all right, based on this and the current state I'm in, where am I going? That's how you can turn that into code. And I encourage you to try it. I'd be happy to help. But this is the foolproof way of counting words. All right. So yeah, I think that is all that I wanted to say about this example. Any last questions? All right, that is officially all that I have for the lecture, for these slides at least. Let's make sure there's nothing else I'm forgetting to give to you. No, it's just the lecture for the day. So I'll give you a new programming assignment, but that will be a problem for Wednesday. Okay?